Hey everybody, welcome back. Today we are starting our new unit and we're talking about topic number 4, that is sets and Venn diagrams. So we're going to start off with an introduction to sets, which we've covered a bunch in geometry already. Our EQ for today is what are sets and what are some special relationships between sets. So in the last unit you learned about some special number sets like the natural numbers, integers, rational numbers, and real numbers. Well, now it's time to expand your work with sets. In this unit you're going to learn the basic language of set theory. You're going to start working with Venn diagrams and learn some of the foundations of basic probability. Now you also learned some of this in geometry, so let's do a review of some basic terminology kind of quickly. So, basic definitions and notation. A set is a collection of objects or numbers, and we call these objects elements. Now, it can be numbers, they can be words, they can be letters, it can be pretty much anything. We use capital letters to identify sets, and then we use braces. They are these curly Q brackets. And the way that you can draw these, think about first draw like a fancy E, but then with like a little extra part, and then you can think about drawing a 3 with a little extra part. That's how I always learned how to do it. You're going to struggle with it, that's okay. Just try your best. Now, the following symbols are used to describe sets, and they are this crazy looking E, which means is an element of. Then there's the E with a slash through it, then that means it is not an element of. Then there's this one, N of A, which means the number of elements in set A. And then if we have just the curly Q brackets, that means it's an empty set. There's nothing inside of it. It has no elements. We can alternatively use the circle or 0 with a slash through it. So you're just drawing the circle with the slash through it, and that signifies the empty set. Let's take a look at an example. Let A be the set of positive multiples of 5. So that A is 5, 10, 15, 20, 25, so on and so forth, right? We know we have a lot of multiples of 5, an infinite number of multiples of 5, in fact. Let B be the set of multiples of 3 between 3 and 30 inclusive. So now we're putting a cap on it, and we're only going to be looking at those numbers 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. We want to know a couple of things. Let's make sure we can read what this says. Is it true that 75 is an element of A? And we'll say, well, yeah, I know that 75 is a multiple of 5, so that is true. Since 75 is a multiple of 5. I'm just trying to get you used to seeing the notation and how we would use it. Next question, is it true that 75 is not a multiple of B? It's hard to see that slash there in that notation, but we'll go in right through it. Is it true that 75 is not a multiple of B? You might start thinking to yourself, well, wait, 75 is a multiple of 30, but it is not a number within this set because we've put that cap on it. So I would say this is true, because 75 is not a multiple of B. While it is a multiple of 3, it is not between 3 and 30. Okay, now we want to let C be the set of numbers that are in both A and B. Let's list out the elements of C. Okay, so to try and figure this out, I like to work with my finite set, the one that actually has a fixed number, and let's see, do we have any multiples of 5 in here? I can see that, hey, 15, that's a multiple of 5, and 30 is a multiple of 5. There are a lot more common multiples of 3 and 5, but these are the only two that are in that set A and in the set B at the same time. Thus, C is the set of elements 15 and 30. Now, let's find the sum of n of B and n of C. So remember, this is how many elements are in B. Just go ahead and count them up. 3, 4, 5, 6, 7, 8, 9, and 10. N of B is equal to 10. N of C is equal to 2. Thus, we could say 10 plus 2, that's the sum, and that is equal to 12. So now that we have an example with multiple sets, we can start seeing relationships between sets. Well, set X is infinite if it has an endless list of elements, and we saw that with set A. That was equal to this set of positive multiples of 5, and it went on and on forever. And we would say that it's infinite because the number of elements in A was infinite. Okay? Now, a set is finite if we can actually have a value, a number associated with n of x. And so B was going to be finite because we had a specific number in that set. It was finite. So that's a finite set. We can also say that two sets are equal to each other if they have the exact same elements and no other elements in them, right? So the order here, however, does not matter. So let's look at the set of numbers 1, 2, and 3, and I know that that is actually equivalent to the set of numbers 3, 1, and 2. The order doesn't matter. We have the same number of elements, and we have the exact same elements. Next up, set X is a subset of Y if every element of X belongs to Y. So it's kind of like one is going to be smaller than the other, and they all have the same value. Okay, and for that we will write using this notation: X is a subset. That's what this symbol means. It means it's a subset of Y. Set X is, however, a proper subset of Y if X does not equal Y. And in that case, we will use this symbol that kind of looks like a C. It almost looks like that is an element of. It's very, very similar. You could start thinking about that. It's kind of like saying that all of the elements in X will be inside this set Y. That's what this really says. Okay, so this is going to say proper subset. And for me, I always remember this connection here between these two symbols. To me, the proper subset symbol looks a lot like strictly less than, and then the subset symbol looks a lot like less than or equal to. And why, to me, why that makes sense is I can look at maybe the size, or understanding that this notation is going to say that all of the elements of X are going to be inside of Y. That must mean X must be smaller than Y. However, if I look at this notation and I see this, I would say that X is going to, all the elements of X are going to be inside of Y, so it must be smaller or at least equal to. It could be possibly equal to, since we have that line underneath it. So they could be equivalent sets, but at least X is entirely inside of Y. And that's how I can understand that notation. Now, let's go ahead and take a look at another example. Let D be the set of letters in the word relates, E the letters in the word slate, and F the letters in the word stale. And you can maybe already start to see where we're going to go with this example. Let's write down N of D, N of E, and N of F. Well, how many unique elements are in D? Okay, unique elements, we have to cross out that second E because that's not the same, or that's one of the same elements. We don't count for the elements more than once. We only do it one time. So there I can see that I have 6 letters in that word, and I would say that N of D is going to equal 6. For slate and stale, we have no repeats, and they are of the same size. So N of E and N of F both equal 5. There are 5 letters in each of those words. Are any of these sets equivalent? Well, we should be able to say yes, because not only are these of the same size, but they actually have the same letters. So let's actually justify that by saying, E is equivalent to F because all of the elements S, L, A, T, E are in this set S, T, A, L, and E. Just because they're in the different order doesn't mean they are not equivalent. So those two sets are equal. Now, are any of these sets subsets of each other? Well, any two equivalent sets will also be subsets of each other. So that means we know that E is a subset of F, and we could also say that F is a subset of E. All the elements of E are in F, and all of the elements of F are in E. Now, let's go ahead and take a look at D. We haven't really looked at that one yet. So D is going to be R, E, L, A, T, and S. And we should recognize that E, L, A, T, and S, those are all of the elements that are inside of E and F. So we could say that E is a subset of D, and F is a subset of D as well. Okay, so all of those are subsets. Are any of them proper subsets? Well, because E equals F, we would say that These are not going to be proper subsets of each other. However, all of the elements of E are inside of D, but there is still one more element in D that is not in E, and that means we would say that E is a proper subset of D. Also, F is a proper subset of D. Let's finish up this lesson by looking at some more set relationships. The first one is intersection, otherwise known as AND. The set of X and Y is written with this kind of cap symbol here. And I always remember which one this is, that this is intersection, because to me that kind of looks like an N. And I say X and Y, that's how I read it. So it includes the elements that are in both X and Y's. They have to be inside of them simultaneously, okay? Now, we can also look at the union of set X and Y, okay? The union of set X and Y is actually written as X or Y. That's how we would read it. So it could be in X or it could be in Y. It could also be in both. That would be acceptable as well. If it's in both X and Y, it's still in X or Y, because it only has to satisfy one of the conditions here. It either has to be in X or it has to be in Y to belong to the union. And the way that I just remember this one, hey, it looks like a U, so U for union. Okay, so important distinctions here that we want to make note of. Since this is either X or Y, almost always this is going to be something that is going to be more inclusive. It's going to include more elements than the intersection is. Okay, it could be that they are identical in size, but this is going to be more inclusive, and then this is going to be more exclusive. And that's kind of hard to get around, because and sounds like you're bringing together more things, and that's not the case when we're talking about set notation. Okay, and is more inclusive, union, or is more inclusive. And is exclusive, union, inclusive. Okay, now another special part is when we see this. Remember, this one is the empty set. If the intersection is empty, then those two sets, X and Y, are disjoint or mutually exclusive. That means there's nothing in common between X and Y. That's all we really mean. It's just fancy math language for saying there's nothing in common between these two sets. No similar elements. Now, the universal set, that's something that we want to a lot of times consider. It's kind of like the starting point of any of our set theory problems. The universal set, which we'll use as the capital letter U, is the set of all elements we are considering in any given scenario. Okay, now we might be considering only a few elements, we might be considering a lot of elements. We might be considering the set of all real numbers. We might be considering only positive integers, right? Natural numbers, something like that. But you always need to have a definition of the universal set when we are looking at these kinds of problems. Now, the complement of a set is written as having a prime notation with it. Okay, it has this little apostrophe, or it has the C as a superscript for complement. Okay, the complement of set X is written as X prime or X complement, and it is the set of all elements in U that are not in X. So it's the set of all elements in U that are not in X. Okay, let's look at some fun facts about these extra relationships. For any set X with the complement of XC, we would say that X and XC are empty. And that should make sense, because here when we're looking at two complements of each other, this is everything in X, this is everything in not X. There should be nothing in common between those two. Okay? However, if we are looking at the union between those two, it's like, well, let's take a look at all of these things and all the things that are not those things. Then that's going to bring everything together. Okay? And then that gives us a huge idea too, that this is like a real foundation of probability, that the number of elements in X plus the number of elements in its complement will always give us the universal set, provided that U is finite. Okay? If we have a finite set, then we can add up these elements. Let's look at an example to try and drive this point home. Let U be the set of digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and let P be the set of prime numbers. Now, you might think, well, there's a lot of prime numbers, right? There's 11, there's 13, there's 17, there's 19, 23, on and on and on. There are an infinite number of primes, but we are only considering the primes that are in this set. So what are the elements of P? Don't forget, 2 is a prime. It's the only even prime. 0 is not prime, 1 is not prime. Okay, but then we have 3, 5, 7, and 9. All of those are primes. Oops, excuse me, 9 is not prime, silly goose. 2, 3, 5, and 7 are all prime numbers. Now, let's write down the elements of P prime. Prime, right? Prime complement, even, if we wanted to think about it in that light. Okay, those elements would be everything that is not one of these. So we've already accounted for 2, 3, 5, 7. Now, this set is going to be everything else. 0, 1, 4, 6, 8, 9. We call these numbers composite numbers because they're not prime, which means we can get these numbers by multiplying at least 2 other numbers. Okay? Now, show that P and P prime are disjoint. Well, all we have to do here, show that, means we have to actually kind of show our work or explain ourselves. Okay? We would say that no element in P belongs to P prime. No element in P belongs to P prime. Thus, they are disjoint. Okay? So you can do that just verbally like this. We could also say, well, let's go ahead and say that x, the intersection between x and x complement, is supposed to be empty. Let's put that in our notation here. P and P prime are empty. That says that those two things are disjoint. Okay? Last one, show that n of P and n of P prime is equal to the n of the universal set. Well, here, n of u, it was all digits. So n of u, excuse me, is equal to 10. My total number of elements in the prime set is 4, 2, 3, 5, and 7. The total number of elements in composite numbers, or non-primes, is 0, 1, 4, 6, 8, 9. That's 6. 4 plus 6 does indeed equal 10. And we have shown that n of p plus n of p prime equals n of u. Alright, that does it for today's lesson. Don't forget to write out your summary, annotate everything in the left-hand column. Thanks for watching, you guys. Have a wonderful day.